Today I am serving as host for a webinar on machining composites entitled Technologies and Strategies for Successfully Drilling, Routing, and Trimming Composite Materials. It will be presented by Mike MacArthur, who is Vice President of Engineering at Robjack Corporation. Robjack, which is headquartered in Lincoln, California, has been designing and producing high-quality carbide tools for more than 50 years. These include end mills, routers, drills, engraving tools, and slitting saws. Mike started as a tool grinder at Robjack 20 years ago, and for many years he served as an applications engineer. In his current position as VP of Engineering, he is responsible for research and development. The webinar today will last approximately 30 to 35 minutes. Afterwards, there will be a question and answer period that will last about 10 minutes. Anytime during the webinar, you can type in and submit a question. Mike will answer as many questions as time allows. If your question is not answered, Mike or one of his colleagues at Robjack will respond to your question via email. The entire webinar will be posted on both the Robjack and Cutting Tool Engineering websites. We will also email a direct link to the webinar to all attendees. And with that, I turn things over to Mike MacArthur.
Hello, everyone. What we're going to do today is talk about the tips and techniques for drilling and trimming of composite materials. We'll talk about tool selection and how to apply those tools to eliminate many of the problems associated with composite machining, which include delamination, uncut fibers, fiber pullout, and poor tool life. I have a couple of videos that I'm going to show, and some of you may see the videos come in a little bit slower than the real-time speed, but we're just trying to show and demonstrate some of the techniques that we're talking about today. So if the video comes through a little bit slower than real-time, just be aware of that as you're watching it. So when cutting carbon fiber, I'll get this a lot where people say, oh, I have a piece of composite or carbon fiber, and what's your best drill or tool to cut that material? When cutting composite materials, there's no all-encompassing solution for all the different types of composites out there. So depending on the characteristics of the material, there's different solutions that work better than others, depending on whether it's a random fiber, a pre-preg composite, whether you have intermediate layers or a vacuum bag process. So when cutting composite materials, it's really important to remember that every material acts a little bit differently. And so the more information a manufacturer has or tool designer has available, it'll really help with making sure we have a solution for your cutting tool needs. As a general rule, when cutting different composite materials, the farther away the weave is to the outside top and bottom surface of the composite, the easier it is to cut. So if you're in the development of the composite material, if you have the ability to change that, which in most cases you don't, if you can get that weave a little bit further away from the top and bottom layer and have a good resin a percentage on the top and bottom, it really aids in drilling and trimming of composite materials. So when cutting composites, rigidity is one of the areas that is often overlooked in optimizing composite machining. And so when the part is vibrating, your tool life is going to suffer. So the more rigid the workpiece is, the longer the cutting tool will last, and the more predictable the process will be. Speeds and feeds will also, you'll be able to go much faster speeds and feeds if you have a nice rigid part and fixturing. It'll also help with predictable tool life when everything is nice and rigid. The most common fixturing is vacuum. And if that vacuum fixture can match the part as closely as possible, it'll really enhance the rigidity of the part. And so I've seen a lot of companies spend a lot of time maximizing the rigidity of their fixtures at the beginning of a run, and then it usually pays huge dividends in repeatability and quality, speeds and feeds, and consistency later on in the process. Sometimes you can't always have a vacuum fixture that matches the part because you're doing a short run or it's not a production type of environment. And so you don't always have to have the high cost solution. So I've seen something as simplistic as having an area of the part that's not very rigid and using sandbags to throw on the part to kind of dampen that vibration, as well as it's pretty common to have a family of parts. So you may have one fixture that many parts go onto, and some of those family of parts may not match that fixture as well. You may have corners that are sticking up off of the fixture unsupported. So some of the solutions I've seen work really well is even just strapping those corners or taping down those corners to the fixture. Anything you can do to help increase that rigidity will really make it a reliable process. So when choosing drills to make holes, typically there's three common types of drills that are used in composite hole making. And the three common are solid carbide, diamond coated, and PCD drills. And so carbide drills are usually only used for like manual operations because of the poor tool life that you get, and usually when you start wearing out those cutting edges, you get really poor hole quality unless you only have to do a couple holes. So in most applications, and we'll focus mostly on the diamond coated drills and the PCD drills for our presentation. When using diamond coated drills, diamond coating is an excellent choice for a drill. And in some applications, you can actually get longer tool life even over PCD drills. And many of the tip geometry that you're able to do on carbide tools, you're able to do for diamond coated, because what we're doing is we're taking a carbide blank, we're leaching out the cobalt at the cutting surface and growing diamond on the cutting edges. So essentially it's a carbide tool that we've grown diamond on the cutting edges to create that diamond coated tool. So you're pretty much limitless on the types of geometries that you could put on there. And so you can see this top tool in this area over here, we have an 8-facet tip, and that 8-facet tip, when you pierce through the material, you'll get a little bit of delamination, and then the double angle there will ream out the hole as you finish the hole to get rid of that uncut fibers, delamination. The middle tool here is more like a traditional 4-facet single angle, and it works with a lot of composite materials, but as you get into the little more exotic materials, sometimes you need different angles to help get those clean holes that you need. This third drill here that looks kind of like a bullet point, what that is it's an elliptical point drill that's used to bring the cutting surface over a larger area of the drill. So instead of a really small area of the drill doing all the hole making, we spread it over a larger area, and then that shape kind of gets rid of the delamination and uncut fibers. So all these drills tend to be really good problem-solving tools when you're trying to make a hole in a composite material, especially carbon fiber, because of the abrasiveness of that. On the PCD drills are an excellent choice for drilling composites and carbon fiber. The PCD tools tend to outperform the diamond-coated drills in higher plastic content materials. The reason for this is they start and maintain a little bit sharper edge because we're actually grinding those edges instead of growing the diamond on the cutting edge from a sharp edge and then growing it on there. On the PCD, we're actually grinding those sharp edges, so the edges are able to have a little bit sharper cutting edge. What's really exciting about PCD in the last year or two is PCD in the past has been really limited on the drills. The two main technologies that were used is you had a flat piece of diamond that was brazed onto the carbide, or you had a vein technology that was a little bit harder to get that raw material and kind of limited in the geometries that you were able to get. You had to make custom veined tools to get that geometry. But in today's technology, we can go in with a solid tip piece of diamond, so that whole black end of the tool is diamond. So we're able to essentially have all the geometries that we had on carbide tools, but now with a very wear-resistant PCD on the cutter. So we're limitless on the types of geometries that we could put onto the tool. So that's kind of a really exciting, and a lot of customers that are starting to use this are seeing huge results with this type of technology, because we can really solve the problems that we had and the void that was there between the carbide and the diamond-coated tools in the past. The other huge advantage of using PCD in a drill application is not only this geometry and the wear resistance of the diamond, but now we're able to resharpen the drill as well. So if that's really important for you to get multiple uses out of it, having this solid diamond, we can put it back in and resharpen the drill as well. So here I'm going to show a video, and remember the video may not show up as full speed on your screen, but essentially what we're doing is we're taking a 1/4 inch, 251 diameter double angle PCD drill. It's going to be going at 233 surface feet per minute, which is 71 surface meters per minute. Or for RPM, it would be 3560 RPM, and a feed rate of about 21.4 inches per minute, and with about a 6,000th per revolution advancement. So to note when you're watching the video is that the holes that we're going to do is to look at the exit hole. We're able to make these holes, very quickly at a fast feed rate with no delamination or uncut fibers at the back side. That little white ring that you're seeing, that's just the dust that's being deposited on there. So as soon as you wipe it off and look at the finished part underneath the microscope, there are no uncut fibers or delamination. So by having those really sharp cutting edges, the really clean geometry specified for composite materials, we're able to cut really clean holes with no delamination or uncut fibers. And you can get typically anywhere from 10 to 20 times tool life over solid carbide. One of the other exciting areas is the engineering and solution for specific problems that you run into when you're cutting carbon fiber materials. And so here's just a couple of the solutions that we've come up with, and many tools can be developed to come up with solutions for your application. For example, the dovetail cutter in the upper right section of your screen here, what that dovetail tool was able to do is when you have a composite part, it doesn't always match the CAD file that you get to program. So a lot of times when you're doing very compound angles or matching up surfaces from one part to the other, a lot of times you'll have to trim the part just to match the CAD file. And then you'll have to come in with these angled tools and things to match one part up to another. But by coming up with a composite, a dovetail tool that can not only put the dovetail but trim the part in one application, and because we make it out of a solid carbide blank, we have the ability to diamond coat it. You get the really long tool life, and we've eliminated operations. So by coming up with a combination tool or a tool that solves a problem, you can save millions of dollars over the production of the part. And in this case, that's what we've done. We've saved numerous hours per part and saved the customer a considerable amount of money. And on the lower portion of the screen, here's an example of a composite reamer countersink. And the threaded type of aircraft drill countersinks have been around for a long time. The problem is you can't diamond coat high-speed steel tools. So if it had a brazed thread on the back, which most tools do, even if they are carbide, a lot of them will be high-speed steel, but if they are carbide, the threads and the back section is usually a brazed-on portion of high-speed steel. By making it out of a solid carbide blank and making the threads out of carbide, we're able to diamond coat it. So it reams, countersinks in one operation, and then you're able to have much tighter tolerances, because whenever you have a brazed tool or you don't have the ability to diamond coat it, you're really trying to chase those tolerances when you're trying to make really tight holes for countersink operations. And one of the tools in this lower right section here is a perforation tool. And this perforation tool is one we're going to talk about a little bit more in a case study for one of our customers. And that's a really exciting tool because we're getting up to 80,000 holes in fiberglass and 40,000 holes with one tool in carbon fiber. And so the application for that style of tool is where you're doing, anytime you have to do really small diameter holes, and a lot of them, common application would be acoustical treatments for aircraft engines in the cells, blocker doors, things like that. In this application, they had to generate 90,000 holes at 50 thousandths diameter in a carbon fiber sandwich structure. And they tested about 10 to 15 different manufacturers, and each of the manufacturers may have had 1 to 5 different types of geometries that were developed to try to solve this problem. And we developed an excellent solution for this. And essentially what they're looking at is when they do these holes, they need very nice part integrity, and the holes need to be nice and round, as well as not have any kind of delamination. So what this is you're seeing all these holes are showing the entrance on the left, exit on the right at 3,500 holes after the tool had cut 3,500 holes. And what you see on this first one here is you see a halo effect around the outside of the entry hole, and that halo effect is actually delaminating that adhesive layer there, and so it affects the integrity of the part. And you can see on the exit that you're getting a little bit of tear out or uncut fibers, and you don't really get that clean cut. And you have a variation of all that. You can see this one actually isn't even that round of a hole, so there's some walking going on. Their part had curvature to it, so some of the drills and other designs had problems with walking and unround holes. But you can see for the solution that we came up with, we get a very nice round hole in the lower right that on the entrance and exit are very clean. And when we looked at the cross-section of these holes, you can see all the different kinds of problems that they ran into. You can see little cracks and delamination of the fibers in the circled area, areas where we have uncut fibers on the top edge. Here's another example of uncut fiber. We had fiber pull-out problems with different types of tools that we came up with. So with the solution of doing these high number of holes with very small diameter tools, we found out there were a couple critical areas to get success. And the critical areas ended up being we had to design the diamond coating to have very good adhesion to the carbide geometry. Because if you have awesome geometry, but your diamond coating doesn't stick to the carbide, essentially you have a very expensive carbide tool. And it's actually even worse than just having a straight carbide tool. So that adhesion was very important to figure out. The other problem that we ran into was we weren't when we first started this testing, we weren't getting the high number of holes and predictability. It was very varied. And when we looked into it a little bit further, and the customer looked into it, we found that the speeder that was used on the spindle was actually lowering the RPM. So it's really important when you're doing applications to make sure that we talked about rigidity in the fixturing, but also the spindles, the speeders that you're going to be using. For this example, the speeder was slowing down, so the feed rates and chip load per tooth was not consistent, and then that was throwing in the variability. So once we switched to a really nice, high-quality speeder, it solved all those problems. The other thing to remember when using diamond-coated or PCD tools is the tool handling aspect. Diamond is very hard, very wear-resistant, but it has brittleness to it. So you don't want to use any kind of contact measurement. You don't want to use micrometers or calipers to measure the tools. You want to use vision systems and things like that to give you non-contact measurement, microscopes, other types of non-contact measurements. And the other thing is handling as well, is to make sure the tools are in tubes, how the operators put them in collets. You just want to have a little bit of a training session with your tool guys to make sure that the handling of the tools are consistent, because if you have chipped tools before they go into the spindle, then you're not going to get the performance out of them. Once we figured out the geometry and the speeds and feeds for the operation and the coating and other areas, this application is extremely successful. Typical speed and feed for doing a 50,000 diameter hole in a carbon fiber part is usually about 50,000 to 100,000 RPM and anywhere from 25 to 60 inches per minute. For our testing, we typically go about 50,000 RPM and 50 inches per minute. When choosing what tools to use for trimming, it's kind of very similar. You have the same type of thing. You have carbide, you have diamond coated, and PCD. For the trimming applications, carbide is usually used if you have an unrigid machine or you have poor fixturing, because the cost of the tool is usually a lot less. And so some of our customers, if they have those applications where they don't have a very rigid setup and they need to do heavy trimming, what they might do is trim with the carbide tool and then come back with a diamond-coated tool or PCD tool just to finish a light cut. If you have a rigid application, you don't have to do that. You can come right in with a PCD or diamond-coated tool and cut in one shot, and you don't have to do that roughing and finishing application. But one of the things we'll get a little bit further in there and talk about is a lot of people will apply carbide tools. They're used to using them at high RPMs and slower feed rates, and it tends to be more of a grinding operation. But when you go over to the PCD or diamond coating, you have that wear resistance, and you don't want that high RPM, slow feed rate application. You want to get in and out of the cut as fast as possible because now you have sharp cutting edges, and it tends to not be as much of a grinding operation. Some of the advantages with carbide is unlimited tool geometries, forms, and then a low cost. But the disadvantage is it's that initial low cost, but high cost for production because you have such poor tool life with carbide in most composite materials that I've seen cases where just cutting 6 inches, the diameter of the tool is already 10,000ths diameter smaller, just cutting a very short distance. So in a lot of cases, it doesn't work very well. You'll have a lot of uncut fibers and tearing of the surface when you only use carbide. When you get to the diamond-coated tools, then pretty much you have the same availability of geometries because anything you can grind on the carbide, you could do the diamond coating as well. And so you have that advantage. But typically, the diamond-coated tools are used in composites for trimming in heavy applications where the carbon fiber is a little bit easier to cut because sometimes what we'll have is, if it's a very difficult carbon fiber, it'll tend to delaminate that diamond layer. So where we said that diamond coated and PCD is excellent for drilling, on the trimming side, we've seen some more successes on the PCD versus the diamond coated, but we do have a lot of customers that use our diamond coated tools for trimming applications. Typically, the diamond coating works better in the lower plastic content composites. When you get into the higher plastic content, the little bit sharper edge of the PCD tends to work a little bit better. The other thing to remember when you get anything diamond coated is the limits on the carbide grade. When you diamond coat, we talked a little bit about it earlier, you leach out the cobalt right on the surface where we're going to coat and then grow the diamond on there. And why we leach out that cobalt is if you don't leach out that cobalt, you'll form a graphite layer before you grow the diamond. So the diamond coating will just wipe right off. So you can't take every carbide tool and just get it diamond coated. It typically has to be a specific carbide grade that's compatible for diamond coating. When trimming, most people use our PCD tools for trimming. The straight flute puts a neutral force on the part, so it's not putting an up shear or a down shear on the part. It works really well if you have that rigid fixturing. They also work really well where you have the sharper cutting edges for your higher plastic materials. It gives you excellent tool life. You have the ability to resharpen the tools. The initial cost for the tool is a little bit higher, but the overall cost ends up being a lot lower. And so if resharpening is important for you or long tool life, the PCD tends to work out really, really well. One of the main things that we have with a PCD failure is misapplying the tool. So a lot of times I've had, when we run into a failure with PCD, is we find out that the customer is using it at the same way that they would use a burr style tool in carbide. They run at really high RPM, very slow feed rate, take lighter cuts, multiple passes, where the advantage with the PCD and the video that we're going to show is typically we can cut right to net shape in one single pass, and there is no need to rough the part and finish the part or use multiple tools. A lot of times when we do this trimming operation, we'll be able to use the tool full depth, one pass, right to size in one shot. And so that saves cycle time and actually reduces the number of linear inches that the tool sees, so it actually gives you longer life. So in this video, it's a 3/8 diameter router and or 9.53 millimeters, and we're going to be going 982 surface feet per minute, which is slower than some of the trimming that I've seen at a lot of places. A lot of times we have to recommend a little bit lower RPM, but then a lot of times faster feed rate. A lot of times people will be going 18,000 RPM with a 3/8 tool or 20,000 RPM, but then going like 20 inches per minute feed rate. So typically we recommend 10,000 RPM, anywhere between the 900 and 1,000 surface footage range, and about 80 inches per minute feed rate, which is about over 2,000 millimeters per minute. So the chip load, it's 8 thousandths per revolution. So this is the video that you may not see that full speed on, but just know that it's going full shot, full depth, one pass, and we're cutting it at 80 inches per minute. So when we cut the material, we're not sitting there rubbing the tool. So some of the advantages of that is we have that nice sharp edge because we have diamond. Then we're shearing the material and not generating a lot of heat. When you grind, you generate a lot of heat. So then you can have problems with melting layers and plastic content. I'll go ahead and play this video one more time so you can see it. The tool goes down one shot, cuts it to shape in one pass, and when you look at this part, these edges are extremely clean, sharp. There's no uncut fibers, no delamination, and we can hold very tight tolerances. In some of the talks that I've done, people are a little bit reluctant on that going to one pass right to size. And in most aircraft applications, that's what I find once you get a good tool and a good operation, you can do. You typically do not have to do any finishing operations. We can hold most tolerances a lot tighter than what is required doing it in that one pass. So on troubleshooting, you know, what tools should I pick? What things can I use for the application on trimming? Most of the time, people are going too high of an RPM. So RPM range, it depends on the material, how much engagement you have. But like worst case scenario, we'll see tools that doing full slots, we can run that 800 to 1,000 surface footage. That's a pretty good range. So for like a 3/8 tool, 8150 RPM to 10,000 RPM, and then the 1/2-inch tool is, you know, around 6,100 RPM, which is typically a lot slower than we see people using the tools. But in our testing and research, you get the longest life, and you really get rid of that abrasive wear out of the tool when run at these speeds and feeds. On the converse side, we see a lot of times people going too slow on the feed rate. So then they're just rubbing the tool, building up heat, and you get premature wear. So to kind of recap, using the right speeds and feeds, the right depth of cuts, you can typically go up to about 2 times the diameter in depth of cut per pass. And then if you cut the parts right to net shape, You really minimize cycle time, and you get longer tool life. On the tool handling side, this is another area where you'll sometimes see failures or people that said, you know, I've tried PCD or diamond coating and it hasn't worked really well. You really need to address the tool handling. You don't want to use any kind of contact measurement, any kind of vision system. If you do have a probe where you're getting your Z offset on the tool, you can do things as simple as using like a plastic shim or even a piece of paper in between the tool and the part, and then just compensate for that. All different kinds of solutions, from high tech to low cost, low tech. A lot of things can work, but you really want to make sure, if you're going to be using PCD or diamond coated or even carbide chips very easily as well, to get that repeatable performance, you really want to concentrate on the handling of the tools. To get the other things is to think of this as a process. We talked about fixturing, we talked about programming and the speeds and feeds and what tools for tool selection to best use. Think of it as a process. When you put together, I hear a lot of people that have many problems with composite machining. If you address the tool selection, the type of tool to use, the programming, the fixturing, the tool holders, all that, it ends up being a very robust system that you know you get 13,000 linear inches out of the tool, and it's very repeatable. And you really can take away a lot of the pains that a lot of people feel in the composite trimming and drilling. So that kind of concludes the slides and the presentation. And now I believe we're going to go to the question and answer session of the presentation.
Thank you very much. That was very enjoyable. And as Mike said, we're going to turn to some questions. The first question we have today is, what type of carbide substrate do you use with diamond-coated drill bits?
So the type of carbide substrate you use is typically a 6% carbide that has either a 1 micron or sometimes even a little bit larger than 1 micron carbide grade. It is a carbide grade that is available out there. It's just most cutting tool manufacturers, if they don't have diamond coated tools in their line, most cutting tool manufacturers kind of use only 1 carbide grade, and it's usually a 10% micrograin. So you're not able to diamond coat that, or if you are, you kind of have sporadic results. So the best carbide grade for diamond coating is a 6%, not sub-micron grain. And if you have any questions on specific carbides, you can give us a call or Crystalloom a call, and there's a list on the websites that you can go to and get what type of carbide works really well.
Okay. All right. Thanks, Mike. Here's another one. Is the diamond tip tool line actually a monocrystalline structure on the tip, or is it polycrystalline?
The examples, I'll go to that slide right now that I showed of these tools. These are not a monocrystalline. These are a polycrystalline. The difference is, in the past, it's been a very thin disc, and so what these are is it's about a 3 millimeter thick, solid pressed diamond on a carbide disc. So we're actually brazing the carbide to the carbide, and we're not brazing the diamond onto the carbide. And so they manufacture the diamond in a disc at that 3 millimeter thickness, so we can put any kind of geometry we want on it. But it is a polycrystalline and not a monocrystalline. I don't know of anyone making the monocrystalline diamond for composite drilling. I could be wrong, but I just personally don't know of any.
Okay. All right. Our third question is, you talk about plastic content, and this question is, what percentage of plastic content would you consider high, and what would you consider low?
You know, that's a very difficult question because I did make a very general statement of high plastic content and low plastic content, but there are other variables in there. It's the weave and the saturation and how loose. What we found is if you have composite materials where the fibers are really not being held by a resin or plastic material, where it almost, once you start cutting it, it almost appears to be like a fabric instead of a solid rigid structure. None of the cutting tools tend to work very well in that kind of environment. So when we say higher plastic content, anything that requires the sharpest edge possible, then the PCD tends to outperform the diamond coated. If you don't need quite as sharp of a cutting edge, and then the diamond coating will sometimes outperform the PCD. So unfortunately, every piece of carbon fiber we get, it tends to be a different solution.
Okay. Okay. Tell you about PCD. This question is about that. How do you form the PCD cutting geometry?
What the PCD cutting geometry is a combination of operations. We use wire EDM. We use EDG, electrical discharge grinding operations. And then we use lapping procedures where we're doing diamond wheels on diamond substrate. So in all those cases, the most of the cost of the tool is the amount of time it takes to whittle away that material.
Okay. Let's see. What type of helix constructions are you able to manufacture with PCD brazed routers?
On the PCD brazed routers, right now it would be a straight flute. There are some technologies out there that I've seen with helical ability, but we've never been able to buy those substrates in production types of volume. So that may be changing or has changed, but in our case, we've never been able to buy enough of that to satisfy our customers. So I would say all of our customers are using straight flute, so there is no helix on the router. When you go to the drill, you're able to put any kind of helix you want because it's a solid piece.
Okay. Now, when you're cutting with the tools, does cold air ever come into play? Is that used to help?
That's an excellent question. You know, we used to have coolant in this presentation, and the problem with that is majority of instances the contractor or manufacturer doesn't have a choice. That's usually dictated, you know, by part design or what piece of aircraft, whether you can use coolant or not. If you do have the ability to use coolant, whether it be a flood coolant or air chiller or anything, even just shop air blowing on it, it does cause environmental issues that you have to take care of. You need to eliminate the dust and any kind of environmental issues that you have. But if you can use coolant, you will actually extend life. If you can use a flood coolant or any kind of air chiller or cold air, we've seen some cases where tool life has gone up 5-fold by just using an air chiller, a cold air gun.
Okay. Well, here's one that's kind of related to wear. Is how many holes can you expect to get with a 1/4-inch PCD drill in CFRP?
That depends on the thickness. So it's usually the number of inches that you can get. But in a typical like 1/4 inch thick material, which is kind of a pretty common thickness, we get, depending on the sensitivity of the part, anywhere between 3,000 and 8,000 holes is kind of a general rule.
Okay. Okay. All right. Does RobJack resharpen these tools?
Yes. The diamond coated, no. The PCD drills and routers and carbide, solid carbide, we resharpen.
Okay. And, you know, kind of related to that is why can't the diamond coated drills be reground?
You can regrind them. When you grow the diamond, we talked about leaching out the cobalt. And the cobalt in carbide is essentially, think of the cobalt as the glue that holds the tungsten carbide particles together. So you're kind of leaching out a little bit of that glue along the outside area of the tool, and then you grow the diamond, and the diamond fills into those voids and kind of encapsulates the carbide, and each of these little crystals grow to make a tiny little like micron little diamond on the surface. And you have all these facets that get in there and to give you that wear resistance layer. And to grow that diamond, you have to put it into a reactor that gets the tools up to very high temperatures. So the whole tool is getting heated to a very elevated temperature, and then we've leached out the cobalt. So the amount of money that you're saving by the raw carbide blank is a pretty low cost. You would have to regrow all the carbide again. You would have to clean up those edges and prep it. And so what we found is cost effectiveness versus reliability. It really hasn't cost justified to do that. So most of our customers choose not to resharpen.
Okay. All right, and we got time for one more question here, Mike. Would you vary your cutting parameters when using PCD versus diamond-coated tooling?
Yes and no. Usually the diamond-coated tooling has more flutes than the PCD typically does. Not to say that's across the board, because we have PCD cutters 1/2 inch diameter with 10 flutes available. So, but in general, most people that are doing heavy trimming with PCD will use 2 flutes or 3 flutes. And then when you go into the diamond coated, sometimes you'll be in 4, 6, 8 type flutes. Speeds and feeds, in a general rule, are about the same, because as you get tighter flutes, you don't have as much room in the flute face to get the chips out. You do have the ability to possibly go 5-10% faster with a diamond coated tool if you had more flutes in there. But if you're taking heavier cuts, the less number of flutes work better. So if you're doing lighter cuts, you can get faster feed rates with diamond coated.
All right. All right. Well, thank you, Mike. That concludes the question portion of our webinar today. And just to wrap things up, as I mentioned earlier, all questions not answered during the Q&A will be answered via email by Mike or one of his RobJack colleagues. And the entire webinar will be posted on the RobJack and Cutting Tool Engineering websites. We will also email a direct link to the webinar to all attendees. And I want to thank you, Mike, for your very informative presentation on composite materials. And thanks to all of you for joining us. I hope you enjoyed it.
Thank you very much.